it's called minimum description length principle. The idea behind it is very simple, right. Among equally, we already looked at it in some form or the other, okay. So lasso is one way of thinking of it as minimum description, right. Among all equally good classifiers, I would like to pick the one that requires the least amount of bits to describe it, right. So the description length should be as small as possible, given that it has some acceptable levels of performance, right. So if you think about it, so what does this tell us? Well, if the classifier is very complex, then I am going to need a lot of bits to describe it, right. If a neural network with a lot of weights, a support vector machine with a lot of support vectors, right, or a decision tree with a lot of branches. So the more information you have, the more detailed the classifier is, the more number of bits I will need to describe it, right. But then the better it gets in performance, right, ideally. And why would you want to make it more complex? Only because it is making fewer errors, right. Then you have to come up with some way of trading off this, the description of the classifier versus the error it makes, right.
What do you mean by description of a classifier?
You have to specify what the classifier is, right? I mean, you have to decide on how you want to specify it. Suppose it is number of support vectors, right. So I will have to tell you what are the individual support vectors. You remember support vectors are alpha times the xi's, right, xi yi, right. So I need to tell you what the xi's are, I need to tell you what the alphas are for me to specify a SVM completely to you, right. So how many bits do I need for specifying those alphas and the xi's, right. So the xi yi I can take it as a product, and I do not have to describe the yi separately, but I need something to describe that, and maybe to describe the alpha also, right, or maybe I can describe alpha xi to you, if you can use that somehow to produce the inner product, right. But if I have it the kernel version of it, then I can't do that, right. So I can't pre-multiply the alpha into that, right. If it is a linear thing, I can do this, I can give you alpha xi. So there are things to think about, right. So how do you encode this, right. So you want to write a program to implement the SVM at the end of the day, right. What is the point in me doing a learning algorithm and then not letting you use it, right. So for me to communicate to you how you implement it, I need to give you the description, right. And the second part is the errors are there, right. So I make some mistakes, right, and I have to tell you on a training set, let us say there is a fixed training set, and on that training set I also want to tell you what are the errors I made, right. The smaller the amount of errors I make, the lesser the number of bits I need to tell you how many errors I made. Make sense? So for me to make small errors, I might need a complex classifier that will need more bits for me to describe the classifier, right. So if I want to reduce the number of bits I want to describe the error, I might increase the number of bits I want for describing the classifier, and vice versa.
So why are we trying to describe the error instead of just having the error rate percentage?
I am sorry?
Why are we trying to get the points that are actually
Just to set up a trade off on equal footing, right. I am just talking about information on both sides now, right. So that is, I can make a classifier arbitrarily complex, right, and it will keep giving me better and better error, right, or I can make a classifier very simple, then it can give me a lot of error. So how do I do the trade off between the size of the classifier and the amount of error I make? So to put these things on an equal footing so that we can compare, right, people talk about the amount of information required in both cases, right. You need some amount of information here and some amount of information here. So the more information you need here, the lesser you need here. So that is the trade off, right. So that is the idea behind minimum description length, right, and there is a huge theory behind it, right. It is actually a proper Bayesian approach, right. We talked about Bayesian learning at some point, we also talked about ML and map estimates and so on and so forth. We can show that MDL is actually a proper Bayesian approach, and people have derived a lot of complexity measures, performance measures based on MDL, right. So I never talked about it earlier, but I think you guys are all ready to now read up on your own about MDL, right. So the brief introduction I gave should be sufficient, right. So if you think just 1 minute and stop and think about how people actually use machine learning, right, it is very heavily empirical, right. We have been doing a lot of math and other things or pseudo math in the class so far, right, but really at the end of the day when you start using it, right, it becomes heavily empirical, right. It is actually a very applied subject, believe it or not. I mean, of course you guys are all finding it out now with all the programming assignments, but it is actually a very applied thing. And so whenever we have this kinds of empirical work, right, so you have to do experiments, right. You really have to do experiments. There is nothing like an analytical solution to your machine learning problem, right. So when they give you a data set, right, you really have to experiment with the data to figure out what is it that you are going to do. So all the theory and everything that we study now is all fine, but when you actually get down to doing something, you have to run experiments, you have to do all kinds of things. So you have to do experiments, you also have to do some kind of exploratory analysis. So in fact we have not really talked about exploratory analysis at all in this course, right. You have to do a lot of different things. So I actually do that whenever I teach my flavor of data mining, I do that. So what do you do with exploratory analysis, right? So there are many things that you have to do. First you have to figure out so how distributed your variables are, so you have to figure out, so what is the range of the variables. So I give you data, right, you don't really know what the data is all about. I just give you the simple form is I give you an Excel file, right. The complex form is I give you like few terabytes of data on a disk, right. But then let us say I give you a file and then you have to figure out what are the different variables that are there, right, and what kind of values do they take, right, and what is the variance of these values, right, or there are outliers on these, is there some values that I can ignore, right. So there are a whole bunch of things that you have to go and do some kind of exploration, right, or there are variables that are important to my prediction, right. So we know about that, we talked about some variable feature selection and things like that, but all of this you have to do. Essentially you have to understand the data before you even think of what is the machine learning algorithm I am going to use. So if I give you some data, you do not just straight away plug it into a decision tree algorithm or straight away plug it into an SVM, right. So you have to go around, try to understand what the data is all about, right. So that is part of it is through exploratory analysis and say a little bit more later, but as far as experiments are concerned typically they fall under two kinds of experiments. So there are manipulation experiments and observation experiments. So what do you think these mean? Right. So in observation experiment I basically try to figure out correlations, I try to figure out associations between variables, right. I make a lot of observations and then I try to say, okay, if this variable, whenever this variable was at this level, then the output was at that level, right. So maybe I can observe the weather. So it is essentially trying to find associations between factors and effects. So what do I do in manipulation experiments? In manipulation experiments, essentially these are things where I have some control over some of the variables that constitute the experiment, right. So typically I set up these kinds of manipulation experiments whenever I want to test a theory, a causal hypothesis, right. Whenever I want to say that A causes B, right. So I cannot stop El Nino from happening, right. So I mean those kinds of that does not make any sense, but I can say something like, okay, so my learning algorithm A is better than my learning algorithm B, right, whenever the load on my system is high, right. So I can actually make a hypothesis like this, right? A is better than B whenever the load on the system is high, right?
Before having your model set, like before making your model, how can you predict that A would be better than B?
No, I have made my models. I have model A, I have model B. Now I want to make a statement that saying that A is better than B. Forget about under heavy load. I want to make a statement that okay, you have a learning algorithm A, he has a learning algorithm B. I want to make a statement that learning algorithm A is better than learning algorithm B. So when will I make such a statement? When can I make such a statement?
From past experience,
Right. So that's the whole thing that we are going to worry about. Here I am going to test what I mean, what I call